So welcome to this video lesson, and we're going to start off by looking at the solutions to the homework problems that I assigned for you to do. So the first one was where we were asked to do the following. It said a nucleus XAZ decays by alpha decay, followed by two successive beta minus decays. Find the atomic and mass numbers of the resulting nucleus. So there are three decays that take place here. The parent nucleus is the XAZ nucleus, and it undergoes an alpha decay, and then it undergoes a beta minus decay, and then another beta minus decay. So let's take a look at how we do this. So firstly, write down the general equation for alpha decay, and that is the parent nucleus will lose an alpha particle, which consists of 2 protons and 2 neutrons, so 4 nucleons. It will have a positive 2 charge. Then what it leaves behind is a daughter nucleus that has a mass number that is 4 less than the original mass number of the parent nucleus, and an atomic number that's 2 less than the original atomic number. Looking at the general formula for beta decay, the parent nucleus, in this case looking here now, the parent nucleus would now be the daughter nucleus from the previous decay. So this nucleus now decays by means of beta decay, and with beta decay we have that a neutron decays into a proton plus a beta particle plus a anti-electron neutrino. So with beta decay, the mass number stays the same, but the atomic number goes up by 1 because one of the neutrons becomes a proton. So Z minus 2 plus 1 gives us Z minus 1. The beta particle has a 0 mass number and a negative 1 charge, and then, as has been mentioned already, there's the anti-electron neutrino, and so that's the first beta decay. Now this daughter nucleus is now going to become the parent nucleus for the next beta decay. So ZA minus 4, Z minus 1. Once again, the mass number stays the same, but the atomic number goes up by 1. So Z minus 1 plus 1 gives us Z. We have another beta particle. We have another anti-electron neutrino. And then recall that the beta particle and the anti-electron neutrino from the previous decay are also there. Therefore, the net decay is from XAZ to A minus 4WZ plus 2 beta particles plus 2 anti-electron neutrinos, and don't forget the original alpha particle that was produced in the first decay. So the daughter nuclei that results from these 3 decays is the WA minus 4Z nucleus. So albeit that we have done this in general, you could be given a specific nucleide or nucleus that decays in this way in a test or an exam, but the method would be exactly the same. This is the second of the 2 homework problems that I assigned to you at the end of the previous video lesson. So this one asks, explain in terms of nucleus structure and stability how unstable heavy nuclides, in other words atomic number greater than 83, may decompose to form nuclides of greater stability if they are below the band of stability, so in other words here, and then B, if they are above the band of stability. So we are going to look now at solving these 2 problems. So if we consider a nuclide, for instance A, that sits around here. So we see that A, if we go down, A's atomic number of protons would be around about 84, 85. We look here, but it's below the band of stability. The band of stability trend should go up there. So notice that A then is sitting in a proton-rich region of this graph, and so it's going to release protons to achieve stability. So let's explain this in detail. So if A is below the band of stability, this implies that it's proton-rich, which implies that beta plus and or alpha decay occur to decrease the amount of protons in the unstable isotope in order to increase the neutron to proton ratio, which would then lead to a higher stability. So in a test or an exam, when you're asked these descriptive questions, it's always good to use bulleted points like I have done here in order to answer the question. Now if we look at a nuclide B that sits above the region of stability, so we're looking there, could be somewhere here, then it's going to be in a neutron-rich region of this plot, which implies it's going to release neutrons to achieve stability, or try and reduce the amount of neutrons in its nucleus. So if we look at answering this, if B is above the band of stability, which implies then it's in a neutron-rich environment, it's on the graph, or it is neutron-rich, then beta minus decay occurs, which decreases the number of neutrons in the nucleus, which leads to a decrease in the neutron-proton ratio in the nucleus, which implies it leads to stability in the nucleus. Now we're going to look at the final type of radioactive decay that we are considering in this course, and that is gamma decay. So gamma decay does not produce particles like alpha decay and beta decay do. Remember, alpha decay produces alpha particles, which are in effect helium nuclei, and beta decay produces either electrons or positrons. Now gamma decay does not produce particles, but what it does do is it produces gamma rays, which are high energy photons, and we represent them as follows. Gamma 00, so it's got no mass number, and it has zero charge. And they travel in vacuum at the speed of light, which is 3 × 10⁸ meters per second. So the general equation is as follows. We introduce this asterisk, which denotes a nucleus in an excited state. So for instance, if we look here we've got a nucleus in an excited state, and then it drops in its energy state to a ground state and releases a gamma photon. So the general equation is X AZ star, or asterisk, decays to a lower energy state of the same nucleus, AZ, plus a gamma photon. So gamma decay usually takes place after alpha decay or beta decay. An excited nucleus makes quantum jumps to lower nuclear energy levels, similar to photons being emitted when excited electrons make quantum jumps to lower energy levels. So if you study further, you will learn about nuclear structure, a nuclear shell structure, the nuclear shell model, where we look at different energy levels within a nucleus, and they are quantized. And so these gamma photons are in effect electromagnetic radiation, as we will go into more detail now. And like visible light, photons are emitted by excited electrons in higher energy levels in an atom dropping to lower energy levels and giving off very specific quantized energy, very specific energy amounts, not just a continuum of energy, but each atom has set energy levels, and so the transitions of electrons between them will have very specific energies. This is true also with gamma decay. So this leads to a high energy and high frequency photon. This should be photon being emitted, and this is according to Planck's energy equation. The energy equals h Planck's constant times the frequency of the electromagnetic radiation. So if we look at this diagram again, we see here we've got an excited nucleus and we have a ground state nucleus. Now, this is a very nice description. It says gamma radioactivity takes place when decay, or an event like a neutron capture, has left the nucleus with an energy surplus. So neutron capture is what happens in, for instance, the initiation of chain reactions when in an atomic bomb or in a nuclear power station, where uranium atom will capture a neutron and then become unstable and then decay. It says the excited nucleus generally returns to its ground state very quickly, and the figure above shows a deformed nucleus rotating about an axis before returning to its spherical shape and losing its rotation momentum through the emission of a gamma ray. The gamma rays are of the same nature as those photons that form the light emitted by atoms, but have energies several hundred thousands of times greater. That's in essence what I referred to just now, just that it's of the energy of the photons is hundreds of thousand times greater than that for visible light. They have alluded to another quantity in quantum mechanics, and that is of angular momentum. And angular momentum also needs to be conserved, like for instance an ice skater who's spinning has got an angular momentum, and then they pull their arms inwards and they start to spin faster. That's in order to try and conserve angular momentum. The same thing happens with nuclei and with other quantum particles. This should be a diagram that you should be familiar with because this was covered in grade 10. This is the electromagnetic spectrum. We start here on this side with very high wavelengths, long wavelengths, which means they have very small frequencies and small energies. And then as we move from radio waves to microwaves to infrared to visible light, the wavelength decreases, but the frequencies increase and the energies increase. So this is actually energy, which is E equals HF. So your frequencies would also increase along here. Then we've got red, orange, yellow, green, blue, indigo, violet in this region. Remember, red light has got a higher wavelength than violet light, but a lower frequency and lower energy than violet light. And then we move into the higher energy part of the electromagnetic spectrum, ultraviolet light, X-rays and gamma rays. So we can see that gamma rays have extremely high energies in comparison to radio waves, microwaves, infrared, ultraviolet and even X-rays. This is an important table that summarizes the properties of gamma radiation. We see that the particle nature of gamma radiation is that it produces a photon, a very, very high energy photon. It's got zero charge, zero mass. The interaction with its surroundings, because of its high energy, the photon ionizes air, creating positively charged air particles, 1 ion per millimeter of air for 2 mega electron volt particles. The range in air is infinite because of its high energy, which means it's very dangerous. So for instance, when an atomic bomb is exploded, the gamma radiation will travel for many, many, many kilometers, doing damage to whoever's in its way. Penetration, several centimeters of lead, ionizing ability high, and once again detected by means of Geiger Miller tubes, cloud chambers, photographic paper. But because it doesn't have a charge, it's not affected by electric and magnetic fields. So it cannot be slowed down, and its direction cannot be changed. I'm talking about a gamma ray now, which would be made up of many, many gamma photons, cannot be altered by an electric field or by a magnetic field because gamma photons just do not have charge. So here's a very nice schematic representation of the 4 types of decay that we looked at. There is another one, also known as electron capture, which is linked to beta decay, but we're not going to discuss that in this course. So you can go and look at that when you do your own research, and you certainly will cover that when you go to university, if you go to university and study physics. So alpha decay, we've already seen this equation. An alpha particle, which is positive, is produced, and if you look here, the Z minus 2 plus the plus 2 of the alpha particle will make the charge Z, which is equal to the proton number. Beta minus decay produces the negative beta particle and an antineutrino, an anti-electron neutrino. Beta plus, exactly the opposite. Beta minus increases the atomic number. Beta plus decreases the atomic number. Here you have an antineutrino, here you have a neutrino that's produced. And then lastly, gamma decay, you have no change in the actual structure of the nucleus. It's still the same nucleus. The number of protons and neutrons stays the same, but it goes from a higher energy state to a lower energy state, and that excess energy is given off in the form of a photon in the region of gamma radiation. Here's another very nice summary, a schematic summary of the types of radiation that we've done, radioactivity, should I rather say. So here's the nucleus of an atom. Alpha radiation, a helium nucleus is given out. If you have beta radiation, then a high energy electron is emitted. And if you have gamma radiation, then a high energy photon is given out, high energy electromagnetic photon. Now here is a very tough challenge, and it's one of those which requires that you integrate knowledge that you should have acquired in other aspects of your science, and that is this problem. One fission reaction of a uranium-235 nucleus, so one fission, it means when a uranium-235 nucleus fizzes or splits, it releases 173 mega electron volts for each decay. So a single uranium nucleus, when it fizzes, when it fissions, when it splits, produces 173 mega electron volts. Now, on that scale, that is a large amount of energy. Estimate the energy released by 1 kilogram of uranium-235. Express your answer in mega electron volts and in joules. Remember, an electron volt, 1 electron volt is 1,602 times 10 to the negative 19 joules. Now, I don't want you just to move on to the solution. I would like you to pause here, maybe even stop the video and work on this. And I'm going to give you a hint. You're going to need stoichiometry from chemistry. So you're going to need to look at the molar mass of uranium-235. You're going to have to look at the number of moles of uranium in 1 kilogram, and then work from there onwards. So give that a go. So here's the solution. So the molar mass of uranium-235 is 235 grams per mole. The mass of the sample is 1 kilogram, which is 1,000 grams. We must work in grams now because the molar mass is in grams per mole. The number of moles is the mass of the sample over the molar mass of the substance. 1,000 grams of sample over the molar mass of 235 grams per mole is going to equal 4,255 mole of uranium-235 nuclei. So now we have the number of moles of U-235 nuclei. So the number of nuclei is equal to the number of moles of nuclei multiplied by Avogadro's number, capital N subscript capital A. So 4,255, notice that I haven't rounded off. Mole multiplied by Avogadro's number, 6,02 times 10 to the 23 per mole. And that gives us that the number of nuclei in 1 kilogram of uranium-235 is 2,561 times 10 to the 24 nuclei. Now when a nucleus of U-235 fissions, then it produces 173 mega electron volts. So the total energy released, if I specify if, all nuclei in 1,000 kilograms, in 1,000 grams or 1 kilogram of uranium fissions, then you would get that the total energy would be the following: 2,561 times 10 to the 24 nuclei multiplied by 173 mega electron volts. That gives us 4,431 times 10 to the 26 mega electron volts. 1 mega electron volt is 10 to the 6 electron volts, so that gives us 4,431 times 10 to the 26 times 10 to the 6 electron volts, which gives us 4,431 times 10 to the 32 electron volts. Note that I still have not rounded off yet. And now recall that 1 electron volt is equivalent to 1,602 times 10 to the negative 19 joules per electron volt, which gives us that the total energy released is 7,091 times 10 to the 13 joules, which is an immense amount of energy. However, it is highly unlikely that 1 kilogram of uranium will completely be fissioned. So we're assuming here that every single uranium-235 nucleus in 1 kilogram of U-235 would be fissioned. So this is a highly theoretical value based on an assumption of 100% efficiency in uranium-235 being fissioned. So now we're going to look at random and spontaneous decay. So radioactive decay occurs within unstable nucleus of an atom or in unstable nuclei. And what happens is the nucleus will emit radiation and it becomes the nucleus of an atom of a different element. That's in the case of alpha and beta decay. And it's important to note that this is a spontaneous process, which means that there's no way, not even in principle, that anyone can predict when a particular nucleus will decay. So we work with probabilities. We look at the probability of a nucleus decaying, but there's no way with certainty that one can determine when a specific nucleus will decay. So all radioactive decay processes are spontaneous and they are random phenomena. So we cannot predict which of a group of nuclei will decay first. For instance, a nucleus of a carbon-14 present in a fossilized bone has exactly the same chance of decaying in a given time period as a nucleus from a freshly chopped tree. So it's a random process. You're going to see in the next video lesson, we're going to use and construct mathematical models and use mathematical models in order to quantitatively describe the decay of certain substances according to certain radioactive decay processes. But we'll look at that in the next video lesson. And also what's very important is that we cannot affect the probability of an individual nucleus decaying, like for instance changing the temperature of an unstable nucleus. So the probability is dependent on the nature of the substance and the nature of the decay process that the nuclide undergoes. So in summary, nuclear decay is a spontaneous process, and it's spontaneous because the decay of an individual nucleus is not affected by the presence of other nuclei, and the decay of nuclei cannot be influenced by a change in chemical or physical temperature or pressure factors. So we cannot manipulate the decay of a particular nucleus in a substance. Just once again, it's important to note that the decay of an individual nucleus is not affected by the presence of other nuclei. So quantum mechanics by its very nature is statistical, and so these processes which are based on quantum mechanics are in themselves statistical. We can also say that nuclear decay is random because it is impossible to predict when an individual nucleus in a sample is going to decay. Each nucleus in a radioactive sample has the identical chance of decaying per unit time, and as I've mentioned, we'll look at this in more detail in the next video lesson. Here is another very important concept in nuclear physics, and that is of decay series. So decay series is where radioactive nuclei decay into other nuclei that are also radioactive, and then these in turn decay further. So for instance, in this particular example, we have uranium-238, which decays by means of alpha decay to thorium-234. Now recall that alpha decay, and we can see here's a legend, so the longer arrows is alpha decay, that with alpha decay that your mass number decreases by 4. We can see here the mass number goes from 238 to 234 because 4 nucleons exist in the alpha particle that leaves the parent nucleus. So the remaining daughter nucleus is 4 nucleons lighter, but 2 of those nucleons are protons in the alpha particle. So the atomic number, uranium is 92, now becomes thorium 90. So there's a decrease in the atomic number by 2. Now thorium in turn then undergoes beta decay. So if we look at beta decay, it's the shorter arrow. So if we look at beta decay, the thorium goes to palladium. And if we look here, remember with beta minus decay, the mass number doesn't change. We've got here the mass number doesn't change. Thorium-234, palladium-234. But what happens is, because one of the neutrons in thorium decays into a proton, then we get an increase in the atomic number by 1. So the thorium becomes a palladium. Remember, with that decay, there's also a beta particle, which is a high energy electron, as well as an anti-electron neutrino. But we're looking here at the resulting daughter nucleus. The resulting daughter nucleus will have the same mass number, but they'll have different atomic numbers, therefore there'll be different elements. And then the palladium goes on to decay to uranium-234, goes to uranium-234, and once again we see there's an increase in the atomic number by 1, but the mass number stays the same. So all along that part of the decay series where beta decay is taking place, the mass number stays the same. But as soon as alpha decay takes place, then we see a continual decrease in the atomic number by 2. You can see it's increments of 2, and so we then find and note that the decreases in the mass numbers is by 4, as we can see, from 234 goes down to 230. This is the number of neutrons, so this is a decrease of 4, but it's going to of 4 in the 4 nucleons, but it's going to be only a decrease of 2 neutrons because there's also been a decrease of 2 protons. So this is an important graph which you will get in your tests and exams, and you will be asked to interpret it. We won't expect you to generate a graph like this unless we give you data, but there are different decay series for different elements. But notice that eventually it lands up through many alpha decays and beta decays, lands up at a very, very, very stable element, which is PB82206. So lead has got a atomic number of 82, which makes it lead. Notice all these isotopes of lead have got the same atomic number. That's why they're lead nuclei, but they have lower mass numbers as they go down. So this is a very light lead isotope. It's not light, but it's light compared to these lead isotopes. So this is a very, very important concept, and we see here that this full decay process is known as a decay series. And so the definition of decay series is as follows. It's the set of decays that takes place until a given nucleus ends up as a stable nucleus, and that is key. The final end point of a decay series is that it's got to be a stable nucleus. And so this one is the decay series of uranium-238. I would like to end off this video lesson with giving you the following homework assignment, and that is to predict by what mode or modes of spontaneous radioactive decay each of the following unstable isotopes might proceed. And by modes we mean alpha decay, beta minus, beta plus, or by gamma decay, or a series of these. So I leave this with you, and I will give you the solutions in the next video lesson.